We now discuss the solution of a problem from the section Differential Calculus, and the problem is on the applications of derivatives. This question has appeared in the joint entrance examination main held on 27th June 2022 in the first shift. The given question is the number of distinct real roots of the equation x to the power of 4 minus 4x plus 1 is equal to 0 is, we are given four options. Option A 4, option B 2, option C 1, option D 0. We are given an equation x to the power of 4 minus 4x plus 1 is equal to 0. Required to find the number of distinct real roots of this equation. That is our given question. We now discuss the solution of the problem in detail. Let f of x is equal to x to the power of 4 minus 4x plus 1. Now, we first take its first derivative. The idea is that we want to find the critical points of this function. So, take the first derivative, f prime x is equal to 4x cube minus 4. We have taken 4 common, 4 multiplied by, in brackets, x cube minus 1. So, to get the critical points, we put f prime x is equal to 0. That will give rise to x cube minus 1 is equal to 0. That will give you x is equal to 1, the only one real root. What happens to the remaining 2? The remaining 2 are given by x square plus x plus 1, but they don't give the real roots. They give complex roots. Therefore, x cube minus 1 is equal to 0 will give rise to only one real root. Notice that f prime 0, right? That means x is equal to 1 is a critical point. To the left of 1, take a convenient point. The convenient point for me is 0. F prime 0 is equal to minus 4, which is negative. And to the right of x is equal to 1, let us take a convenient point x is equal to 2. Then f prime 2 is equal to 4. Yeah, f prime x is 4 times x cube minus 4. So 4 into 2 cube minus 4, which is positive. So f prime 0, that is 0 is to the left of 1. F prime 2 is the right of 1. So from this, fx is strictly decreasing in minus infinity to 1. Minus infinity to 1, it is strictly decreasing. And fx is strictly increasing in 1 to infinity because f prime 2 is greater than 0. Right. So fx will strictly decrease in the interval minus infinity to plus 1 and strictly increases in the interval 1 to infinity, and hence fx attains minimum at x is equal to 1, and f min, that is the minimum value of f, is given by f of 1, that is wherever there is x you substitute 1. So 1 to the power of 4 minus 4 into 1 plus 1. That is equal to minus 2. So the minimum value is minus 2. So now, while fx is strictly decreasing in minus infinity to 1 and attaining f min at f of 1, that is minus 2, that is the graph of fx crosses the x-axis exactly once. Why exactly once? Why this word exactly? Because it is strictly decreasing. So fx is strictly decreasing in minus infinity 1 and attaining f minimum value at x is equal to 1, namely minus 2. minus 2. Therefore, the graph of fx crosses x-axis exactly once. It is exactly because it is strictly decreasing. In a similar fashion, while f of x is attaining f minimum value f of 1, that is equal to minus 2, and is strictly increasing in 1 to infinity. Therefore, the graph of f of x crosses the x-axis exactly once. This is exactly because since it is strictly increasing. So, from this analysis, we conclude that thus f of x is equal to 0, the equation has two real roots. Where are these two real roots? One real root is in the minus infinity to 1, and the other real root is in 1 to 2, 1 to infinity. One real root is in minus infinity to 1, and the other real root is in 1 to infinity. So, where are they exactly? This analysis doesn't say, but it will conclude that it has two real roots. So, let's look at our options. It has two real roots. That appears against option B. Therefore, the answer to this question is option B. So, that is the detailed discussion of the solution of the problem on the applications of derivatives. But I will continue this discussion further in the next slide, and I want to tell you that where exactly, because minus infinity to 1 the root is there, but minus infinity to 1 is a big, it has an infinite length, and where exactly it is at least slim down the length of this interval, so also slim down the length of 1 to infinity. So, we will do that in the next slide. So, this is what we have done. So, f of x is x to the power of 4 minus 4x plus 1. We have seen f of x is strictly decreasing in minus infinity to 1. F of x is strictly increasing in 1 to infinity. F of x attains minimum value at x is equal to 1, and the minimum value is minus 2. From this analysis, it follows that f of x is equal to 0 has exactly two real roots. One root lies in minus infinity to 1, and the other root lies in 1 to infinity. We want to slim down these intervals. So, we will now show that one root lies in 0 to 1 and the other root lies in 1 to 2. The open interval 0 to 1 and open interval 1 to 2, and one root lies in open interval 0 to 1 and the other root lies in the open interval 1 to 2. For that, we will take the help of the intermediate value theorem. For that, we see f of 0. So, that means x is equal to 0, you substitute. 0 power 4 minus 4 times 0 is 0 plus 1, 1. So, 1 is positive. F of 1. So, if you substitute 1 minus 4 plus 1, this is minus 2, which is negative. So, f of 0 is 1, which is positive. F of 1 is a negative. So, and f of x is a continuous function. By intermediate value theorem, there exists a root in the interval, open interval 0 to 1. And we see f of 1 is equal to minus 2, which is a negative, yes. F of 2, x is equal to 2, you substitute, and that will be 9, which is positive. So, f of 1 is negative, f of 2 is positive. Therefore, by intermediate value theorem, there exists a root in the interval 1 to 2. So, we have slimmed down minus infinity to 1 to 0 to 1 and 1 to infinity to 1 to 2. Open interval 1 to 2. So, by the intermediate value theorem, f of x is equal to 0 has exactly one root in 0 to 1. Why this exactly? It's again it is strictly decreasing. Exactly will come because of the strictly decreasing and increasing nature, and f of x is equal to 0 has exactly one root in 1 to 2. Why exactly? Because it is strictly increasing. Agreed. So, thus we have slimmed down this the existence of the roots rather than in this big intervals to small intervals. So with this analysis, I can now visualize the graph of f of x is equal to x to the power of 4 minus 4x plus 1. So that is your x-axis and y-axis, and your graph of f of x is decreasing, and attains minimum at x is equal to 1. The minimum value is minus 2, and it increases further in the interval 1 to 2 and 1 to infinity also increases and crosses the x-axis here, and while decreasing it crosses the x-axis here. And it is exactly why, because it is strictly decreasing here, it is strictly increasing here. Thus you get the answer exactly 2 roots, and the graph can be visualized like this. From the first analysis in the first slide what I have shown, I cannot give you guarantee that it crosses x-axis, that's all. It crosses x-axis somewhere here, somewhere here, and here pinpointedly I say that it lies between 0 to 1, and this root will lie between 1 and 2. So that is the detailed analysis of the discussion of the solution of the problem, which is based on the applications of derivatives. So I am sure that you have understood the solution of the problem and its extension and its graph, and I wish you all the best. Thank you.